Hi guys, today we will be discussing a well-known equation in the field of quantum physics, the Schrodinger's equation. The Schrodinger's equation created a revolution in the field of quantum physics. It was developed by Erwin Schrodinger in the year 1925. He worked on the principles of wave-particle duality which was put forward before. We know that the total energy of a particle is equal to the kinetic energy plus the potential energy. We also know that the kinetic energy is equal to half mu square, whereas we can say the potential energy as V. Now we know that the linear momentum P is equal to m times u, where u is the velocity. In this case, it's the speed of light. When you square this term, we get p squared equals m squared times u squared. When we substitute this u squared equals p squared over m squared to the kinetic energy equation, we can obtain that half m times p squared divided by m squared. This is equal to the kinetic energy. Now we can simplify the energy equation to E equals, where E is the total energy, P squared divided by 2m plus the potential energy V. We know that the wave function psi x, in this case we consider the time also, so psi x comma t is equal to e to the power I k x minus omega t. This is the general equation for the wave function. When we derivate this with respect to x, we can obtain that d psi x comma t with respect to x dx is equal to I times k times e to the power ikx. We only consider the x term here because we derivate it with respect to x. So the time or the t function is not present in this equation. Now we derivate it again with respect to x. So d squared psi x comma t, this is the second derivative, over dx squared is equal to I times k times I times k times e to the power ikx. Now here we can simplify it further to I squared times k squared times e to the power ikx. We know that I squared, this is a complex number, this is equal to minus 1. So we can simplify it further to d squared psi x comma t over dx squared is equal to minus k squared e to the power ikx. Here the term k is again the wave number. We know that the wave number k is equal to 2 pi over lambda. We also know that lambda, where lambda is the de Broglie wavelength, is equal to h over the momentum p. Now when we substitute this lambda to this particular equation, we can see that k is equal to 2 phi divided by h over p. We know that h hat is equal to h, which is the Planck constant, divided by 2 phi. So this particular equation is simplified down to p equals h hat times k. So k is equal to p over h hat. Now we substitute this p over h hat to the equation we found before. It is d squared psi x over dx squared equals to minus k squared times psi x. When you substitute this here, we can obtain that this is equal to minus p squared divided by h hat squared times psi x. This is the second derivative. We know that the energy E is equal to P squared divided by 2m plus the potential energy V. Now when we multiply both the sides by the wave function, we can obtain the equation E times psi x is equal to P squared divided by 2m times the wave function psi x plus V times psi x. Now when we apply the derivative term or the second derivative we obtained before on this particular equation, we can see that this is simplified further down to E times psi x is equal to minus h squared divided by 2m times the second derivative E squared psi x over dx squared plus V times psi x. This is only considered with the x direction without the time simple t. So we can say that this particular equation is time independent. Schrodinger said that this particular equation is known as time independent Schrodinger equation. The time independent Schrodinger equation is minus h hat squared divided by 2m times the second derivative d squared psi x over dx squared plus V times psi x, where V is the potential, is equal to V times psi x. This is the time independent Schrodinger equation. We know that E is equal to hf, or rather h hat omega. This is because we know that h hat is equal to h over 2 phi. We also know that the wave function we obtained is equal to psi x comma t is equal to e times I to the power ax minus omega t. The energy equation we obtained before can be multiplied by the wave function. So we can obtain that E times psi x comma t is equal to my h hat omega times psi x comma t. When we simplify this further with the equation we obtained before, we can see that this becomes I times h hat times this first derivative of psi x comma t of the wave function over dt. Now we know that the wave function times the energy p times psi x comma t is equal to minus p squared divided by 2m times the wave function psi x comma t plus v times psi x comma t. Previously we obtained this particular p squared over 2m with respect to the second derivative of x. So we can now obtain the equation minus h squared divided by 2m times d squared psi x comma t over dx squared plus v times psi x is equal to this particular ih hat term with the first derivative of time. So this is ih hat times d over dt psi x comma t. This was defined by Schrodinger as the time dependent Schrodinger's equation. So today we discussed the Schrodinger's equation, and that Schrodinger put forwarded two particular situations with time independent and time dependent. This was only with respect to the direction x. So he developed the equation in 3 dimensions with x, y, z coordinates. Thank you for listening.